Okay, doing a second video here on chase problems. I thought the first one was getting long enough. This is a situation where we have two objects that are covering a related amount of distance in a related amount of time. What's very common in these situations is that they actually are covering the exact same distance over the exact same amount of time, and you can imagine this is like one object is trying to catch the other object. That's why we call it a chase problem. But one object doesn't have to be chasing the other object. They don't even have to be going into the same direction or anything like that. To take this approach, what we really need is there to be some sort of mathematical relationship between the first and the second object and their distances and times. So this is a straightforward one to get us started. A child leaves his house headed for school without lunch. He travels at a constant speed of 3.0 meters per second. After 90 seconds, his father realizes the child did not take his lunch and chases with a speed of 5.5 meters per second. Using a graph, find out how far the child gets before his father catches up with him. I'm going to make a sketch here, and then I'm going to explain why, for this particular graph, I'm going to jump over to Excel, because the numbers are just going to be getting to a point where it's much easier to look at it on Excel. If I make this like 30, 60, 90, 120, and so on, and then the boy is going to go like, I'll use green for the boy. He's going to go like 90 in the first 30 seconds, and then he's going to be up to 180 in the second 30 seconds. And what we can see, I just add one more 0.270 after the next few seconds. What we can see is that the numbers are getting very large very quickly, and they sort of fly off here. The father, on the other hand, is going to go about 165 meters in 30 seconds. He's going at 5.5 meters per second for about 30 seconds. That works out to 165. And what you can see here, if we try and make these graphs, is that it's going to be, especially sketching by hand, a pretty inaccurate view of where that intersection point is. If you try and use it and come down to this axis, you might come up with some number that you have for where they meet up, where the position of the father and the child have come to the same location, and come up with that time. But it's going to be pretty hard to make a really accurate prediction based on that. We're on a computer, so we can go to Excel very easily. And I thought this is as good of a time as any for me to show you some of the nice functions of Excel. So if I'm dealing with time here, 0, 30, 60, 90, one of the nice things that Excel can do is it recognizes a pattern very quickly. So if you put all those in, you can highlight them and grab the little square in the corner and drag it down, and it's going to autofill with all of the numbers that follow the pattern that you're using. Now the child, we said, starts at 0, and he's going to go 30 times 3, or 90 meters in the first second, 180 in the second, 200 in the next section, and another 90 in the third. He's going at a constant speed here. If I highlight all those and I drag them all down, well, there I go. I have all of the boys' positions for a large period of time. Now the father isn't going to start moving until 90 seconds. So at 90 seconds, he's still at rest. But we said he's going 30 times 5.5, or 165 meters per time. So 165, add another 165 to that, add another 165 to that, and we probably have enough of a pattern for Excel to recognize. Highlight the part that has the pattern and drag it down, and we get our result here. Now visually on this, I can see that my intersection is going to occur somewhere just before 210 seconds. See, the child's at 630 meters, and the father's all the way up to 660 meters. So I don't need most of this stuff. I'll go ahead and make a graph of this. If I go Insert, always use a scatter plot in physics. And here we go, and we can get an idea. Series 1 here would represent the boy, and Series 2 here would represent the dad, and that is fairly in line with the sketch that I've made, but I would trust the numbers on this much more accurately. Now, I don't usually do this, but if I go to my graphing type, here, you know what, I'm just going to get rid of it entirely. Do that again. I'm going to highlight them, and instead of using the XY scatter, which is just the dots, which is what you should be using most of the time, I'm going to use this sort of broken line thing. And what I can do is I can get a more accurate view of where that actual intersection point is happening. It's not giving me the point, it's saying 180 and 495. So I wonder if I can write on this. I don't think I can. No. What I have to do is I have to imagine extrapolating that line straight down. What if I'm going to see if I can put this whole graph into my OneNote file here. There it is. So now I can draw on it. So what I want to do is I want to come straight down from that value. And it looks like I'm dealing with something very close to 200. Let's call it t equals 195 seconds. I don't know about you, but it's better, but it's still not a perfectly accurate answer, and it strikes me that there's probably a way to get the exact answer. So let's, instead of looking at a displacement time graph to try and solve this problem, let's look at a velocity time graph. Here, I can imagine the child, who I've been working with in green, traveling along at 3 meters per second out to some undetermined time t, and we're going to assume that t is where he gets caught. Here we're going to, let's make that 30, 60, 90, and then all of a sudden after 90 seconds the father realizes the issue and starts chasing along. He's going to chase along until that same time t. Now, how is this useful? Well, we want the displacement of the two objects to be equal to one another. So what we can recognize is that if the displacement is the area under these curves, if their displacements are going to be equal, then the red and green shaded areas that I just wrote are going to be equal. So the displacement of the father has to be equal to the displacement of the child, and that means that the area of the red curve has to be equal to the area of the green curve. Okay, so to get those areas, I have to use that unknown t, and I'm going to have to get a base and a height. The height, it's actually, or length times width, whatever you want. It's actually rectangles here, so it's a little bit easier. Length times width equals length times width. For the, if I want to call this the length, for the father, he's running until sometime t, but he didn't start until 90 seconds. We have to subtract away that 90. He's traveling at a speed of 5.5 meters per second. For the child, he gets to travel that whole time t, but only at a speed of 3.0 meters per second. If I solve this equation for t, where the two areas are equal to each other, I should get the exact answer of where the child is caught. Distributing that 5.5 into the brackets, I end up with 5.5t minus 495, and here I get 3.0t. I move the 495 over to one side, and the 3.3t over to the other side, 3.0t, and I get 2.5t, a little sneak peek at the answer there, divided by 2.5, divided by 2.5, and I get a time of 198 seconds. That corresponds well with our guess at about 195 seconds up here, but I trust this answer a lot more. It's algebraic, and I know that it has to be true if those two times are going to be equal to each other. So that's a chase problem. We'll do more chase problems algebraically. We may do a couple more with graphs, but they're fairly challenging, so we're only going to, we're just getting started on those.